covered the last video, alright, in sampling and hypothesis testing, part 3. So make sure you already cover the first and second video. So this video will cover hypothesis testing. So these are the few, the one that we will cover later on, 2.1, 2.2, 2.3, hypothesis testing, what is null and alternative hypothesis, what is significant levels, critical region, mean for normal population, testing population mean, and testing population proportions for small and large sample. Okay, so for hypothesis testing, hypothesis test, okay, so the first thing you have to know is what is null hypothesis. Null hypothesis we denote as H0, and alternative hypothesis is we denote as H1. Okay, alternative hypothesis H1 is the one that you claim or believe that we wish to establish. So these are the definition. Null hypothesis is the opposite statement that nullifies the claim. Okay, so let's look at the example. Consider the following example. So you have an electric company claims that its electric water heater has a mean lifespan of more than 800 hours. If mu represent the mean lifespan of the electric water heater, then we can formulate two hypotheses as follow. Okay, so H0 is given by mu equals to 800. H0, and then the one that you claim is this one, is more than 800, so mu greater than 800 hours. Okay, so H0 null hypothesis, a specific value of the population parameter mu that is 800 hours. Alright, this is also the hypothesis that electric company hopes to reject. Okay, and then H1 alternative hypothesis, it states a range of values of mu, that is mu is more than 800 hours. Okay, in any hypothesis test, H1 indicates whether the test is one-tailed or two-tailed. Okay, H1 which propose a change in one direction yield one-sided or one-tailed test. H1 which suggests a difference in either direction yield a two-sided or two-tailed test. Okay, this is how we differentiate both. Okay, and then for hypothesis test, on the population mean mu, the null hypothesis propose this value. Mu equals to mu naught. And then alternative hypothesis may take any of the following three forms. Okay, so mu less than mu naught one tail test for a decrease, mu greater than one tail test for an increase, and then mu not equal to mu naught is two tail. We test for both sides. Okay. Alright. So now let's look what is significant levels and critical region. Okay, a test statistic is a value calculated from a sample data to determine whether we accept or reject our H0. Okay, for example, consider a population of mean mu and standard deviation 70, which is normally distributed with 80 and 70 square variance. Okay, and then our H0 is defined by mu equals to 800, and then our H1 is mu greater than 800. Okay, this is based on the previous, the first example just now. Okay, the sampling distribution of X bar is normal. Okay, from that population, you take out your sample and we assume that H0 is true, and then our X bar is also normally distributed by 800 mean, and then the variance is sigma square over n. Still remember from the previous video, sigma square over n. And then our standardized test statistic is given by Z, where your X bar value we minus with the mean and divide by standard deviation, where your Z is already standardized, where your mean is 0 and standard deviation 1. Okay. To test H0, we take a sample of 50 from the population. Okay, so we use that example just now. Then we calculate the standardized test statistic, and we just substitute just now is X bar minus mean and 100 divided by 70 divided by 50. This one should be set n, kan? So n is 50. Then we calculate the value. Okay. Significant level of a test is the probability of rejecting hash node when it is in fact true. Critical values depends on the significant level and also whether the test is one-tail or two-tail. Okay. If the value of the test statistic falls in the critical region, then hash node is rejected and hash1 is accepted. Okay, this one, please take note. When you find the value of z, and then this value of z falls in the critical region, then we will reject our hash node and we accept our hash1. But then if the z value that you have calculated here using test statistic and then falls outside our critical region, then it will be we will accept hash node and reject hash1. Lebih terbalik. Okay, in order to prevent as far as possible any false claim from happening, the significant level is made as small as possible. Okay, so the table below gives the z values corresponding to various significant levels of alpha. Okay, so these are the thing. This one is taken from the specific value from your normal distribution table. Okay, so for example, our critical region is 1% level of significant. So 1%, 1% is 0.01 here. 1% is this one, 0.01. So our Z is 2.326. Okay, so you see our critical value, our Z value is 2.326. Okay, so the shaded one is the rejection region. So when you find the Z value, when you calculate test statistic just now using the formula, and then you get the value of greater than this value. So if greater than this value, meaning that we will reject our hash node and we will accept our hash1. Same thing, if less than, then you have this on the left hand side. This is we call as one tail test. If two tail, meaning that you consider both. Okay, like this, two tail. So here is 5% critical region. 5% is the summation between two sides. Okay, so you will have to divide by 2. So 5% is 0.05. So left hand side is 0.025 and then the other side is 0.025 as well. Okay, 1.960 is difference on the table just now. Okay, and then, okay, so these are the conclusion. If we reject hash node, then hash1 is true. If we accept hash node, then hash1 is true. Then we will reject the other one. Okay, you cannot accept both. You have to reject one, accept one. Okay, let's look at an example. In each of the following cases, given the population standard deviation sigma, the statement of a claim about mu, sample size, and a level of significant alpha. Okay, so alpha here is our level of significant. Formula. Okay, the first one, you have to find what is the null and alternative hypothesis, the statistic, and what is the rejection region. All right. So the first one is this is our claim, right? The first one, claim mu greater than 3.5. So that one is our H1. Then our H naught will be equal sign mu equals to 35. So we will get this. So H naught is our null hypothesis, H1 is our alternative hypothesis. And then you have to find the Z value, standardized test statistic. So X bar from your sample minus mu over 2.5 divided by cert 65. Okay, sigma over cert n. And then you found out the test statistic. And then rejection region here is based on your alpha. Alpha is 0.01. So 0.01 is, okay, 0.01 is 2.326. So that's why our critical value is Z equals greater than or equals to 2.326. Okay. If here is greater than or less than, then we just consider one side. If greater than, you use the right hand side. If less than, you use the left hand side. If B not equal, then you have to consider both sides, two-tailed test. Okay, same thing. So this one, 1.96. So this is for alpha equals to 0.05. So 0.05. Why does it 1.96? Because 0.05 for both sides. So one side is 0.025, the other one is 0.025, the critical region, rejection region. Okay, let's look example 2. A random sample of size 64 is taken to test the claim that mu greater than 20. So this is your hash 1. Okay, it is known that standard deviation sigma equals to 5. If the rejection region is set by x bar greater than 21.028, what is the level of significance of the test? And then find the numerical value of C so that test of with the rejection region x bar greater than C has a 1% level of significance. Okay, how to find A? Okay, first, what is our null hypothesis? If here is our H1 and H1 mu greater than 20, meaning that our H0 will be mu equals to 20. Null hypothesis is always equal to. Okay, so since this is greater than, so meaning that we will use one tail test on the right hand side. It's greater than towards to the right. Okay, this one. All right. So this is our alpha that you don't know what is the alpha value, but then you know the critical value is 21.028. Okay. So this is your x bar value here. So using test statistic, you want to find that z. What is the value z here? Okay. So 21.028 minus 20 divided by 5 sigma over 64. This is our n. Okay. And then you get 1.645. Okay, so 1.645 is 0.05 alpha. Okay, 1.645 is this one. This is our Z. So the probability will be 0.05. So the level of significance of the test is 5%. Okay, so at first at 1% level of significance with rejection region x bar greater than this C. Okay, so alpha what 0.01, so 0.01 is this, and then based on the alpha we can find our z critical value. Okay, and then now we want to find what is our x bar, so which is greater than C. So greater than C, C minus 20 over 5 set n equals to 0.01. Then because this is our z kan, C is our x value, so C minus 20 we standardize using test statistic, and then since we know the z value is 2.326, then we equal both sides, so you can find the value of C. So C equals 21.454. Okay, 0.01 is this 2.326. All right, so settle for first part, how to identify your hash node, how to identify your hash one, and why are we using one tail test and two side tail test. Okay, and then how we can reject, how we can accept our hash one or our hash two. Okay, now move on to testing population mean. So these are the general test procedure. Okay, first you have to state what is your hash node and what is your hash one, and then state your significant level. Okay, your alpha, and then you have to calculate your critical region. Then you have to determine your critical region whether your Z is fall on your critical region or not. Okay, and then after you identify, then you have to make a conclusion. Okay, remember from the previous slide just now, if the value of your test statistic Z falls in the critical region, then hash naught will be rejected as you will accept hash 1. Okay, remember that one, the one that I highlight red color in the front slide. Okay, mean of the normal population with known variance. Okay, now you want to find the mean for normal population and you know what is the variance. Consider a normally distributed population with unknown mean mu and then variance sigma square. Now we have H naught, mu equals to mu naught. Okay, so take note, our H naught is always equal sign, but our H1 can be less than, greater than, or not equal. Okay, so if less than, meaning that we will consider one tail test on the left side. If greater than, one tail test on the right side. Okay, if not equal, then you have to consider both side, left and right side. Okay, since the population is normally distributed, then your sample x bar is also normal with mean mu naught and variance sigma square over n. Okay, then you have this. X bar is normally distributed mu naught sigma square over n. Then you standardize minus mu over standard deviation. Then your standardized test statistic is given by this formula. Okay, you have to memorize this formula. Okay, now example. The mean lifetime of electric bulb produced by a given process is 1200 hours. Okay, to test a new batch, a sample of 80 shows a mean lifetime of 1175. Okay, so our H naught here is mu equals to 1200. Since they want to test a lifetime of 1175 hours, meaning that the mu for H1 will be mu not equal to 1200, unless they say that they want to show a mean lifetime greater than or less than, then you use greater or less than, but they stated the value there, so you have to put not equal. Okay, assuming that the lifetime of the electric bulb is normally distributed with standard deviation 120 hours, test the hypothesis that the mean lifetime of the electric bulb has not changed using the level significant of 0.05. So that is your alpha. Okay, look at the figure here. Because this is not equal, so they consider both sides. Okay, 0.05 for both sides, meaning that one side is 0.025 and then the right hand side is 0.025 as well. Okay, and then you test the statistic. Test statistic 1175 minus the mean, and then divide with 120 standard deviation over sample, set of sample, then you get this negative 1.863. Okay, so negative 1863, this z value falls outside the region of the shaded one. Okay, meaning that this value is not fall on the rejection region. So since it is not fall in the critical value in the rejection region, then we cannot reject our H naught. Okay, meaning that we will accept our H naught. Okay, we will accept our H naught and we will reject our H1. All right, understand? Because this value negative 1.863 is somewhere here, which is outside, somewhere here, right? Somewhere here outside and far from the rejection region. So that's why we will accept H naught. Okay, all right. Okay, next example. Sample size of 25 is taken from a normal distribution with mean mu and variance 16. A hypothesis test is carried out at the 1% level of significance. On the basis of the value of the sample mean x bar, the null hypothesis mu is given by 200 is rejected in favor of the alternative hypothesis mu greater than 200. What can be said about the value of x bar? Okay, so we know that H naught is mu equals to 200. Then our alternative hypothesis mu greater than 200. Then we will consider one tail test on the right side. And then they say that H naught is rejected at 1% level, which means that your test statistic here will be greater than 1%. 1% is this, kan? 2.326. So we will reject if your Z is greater than this value. So since they reject, okay, since our H naught is reject, meaning that your Z will be greater than this value, all right? So we want to find that X, what is the X value? Okay, so x minus 200 over 4 divided by SURT25 is greater than this. So this is our critical value that identify this one. Now we have to find that x bar, and then you arrange everything and solve. You found that x bar greater than 201.86. Okay, since H0 is rejected, meaning that the sample mean will be greater than this value. Okay, will be greater than this value. Okay, now mean of non-normal population with known variance. Just now is mean with normal population. So what if the population is not normal? Okay, the probability of x bar is not normal for all sample size. However, the sample size n is sufficiently large, then by central limit theorem, okay, we will call back from the second video. Okay, for non-normal population with mean, mu, and variance by central limit theorem, we will define as this, right? X bar from our sample, normal, mu, sigma square over n, provided that sample size is large. How large is that? It's at least n greater than 30. So this is your test statistic. Okay. Okay, move on. Mean of population with unknown variance. Just now, normal population with known variance, and then non-normal population with known variance. But then this one is unknown variance. So it's the same, okay, but a bit different formula to find the unbiased estimate for a large sample taken for a normally distributed population with unknown variance, and unbiased estimate for sigma square used in a statistical test is sigma bar square, where sigma bar is given by this. Okay, if the large population is not normal, then the central limit theorem can be applied since the sample size is large. Okay, so in both cases it is the same. Okay, x bar minus mu, no, the formula is the same. The test statistic also. Okay, let's look at an example. The mean height of a student's population, which is believed to be normally distributed, is 165 cm. A sample of 60 students is taken and the mean height is 165 cm with standard deviation 3.8 cm. Okay, can it be reasonably regarded that in the population the mean height is more than 165 cm using a level of, okay, of this one, not all s, of significance of 0.05? Okay, so these are our solution. Our hash note is mu equals to 165 cm. All right. Hash 1, mu is greater than 165 cm. Why? Because they want to check this one. The mean height is more than 165 cm. So this is our hash 1. Our level of significance is 5%. 5%. Then since this is, you don't know what is the the variance is with unknown variance. So this is unbiased estimate of sigma. So sample sigma square is given by this formula. Okay, you have the standard deviation of the sample, but you don't know what is the standard deviation for the population. So you have to use this formula. Okay, so 60 over 60 minus 1 times 3.1 square, then you get the unbiased estimate of standard deviation. Okay, and then using our formula test statistic, then you sub in the value, then you get your z is 1.617. All right, so our significant level of significance is at 5%. Since this is greater than, then you test on the right side only. Okay, 5%. Okay, 5%. So 5% is, oh, I didn't give the table there. So 5% is this value. Okay, 5%. 1 point, the reject level of significance is 0.05. Then the z value is 1.645. Okay, if this z value falls inside the shaded region, then we will reject our hash node. Okay, we will reject our hash node. But then, since this Z is 1.617, which is somewhere here outside the shaded region, outside the critical rejection region, then we say that there is no evidence to reject hash node. So we have to accept that our hash node. Okay, understand? Huh? All right. Okay, next. I think this is the last part. Okay, we make it fast and simple. Okay, testing population proportion. Okay, for small sample, there are two types, small sample and large sample. Right? For small sample, it must be fixed number of n trial independent, only two outcomes, success and failure, and probability of success P is constant for each trial, and this is to find the probability. Right? What distribution that you will think about when it is only come out with success and failure? It's binomial, right? Binomial distribution. Okay, let's look at an example. Mr. Tan is standing for election and he claims that he has 60% of the electorate prepared to vote for him. Okay, claim. An investigator thinks that Mr. Tan overstating his case. The investigators select a random sample of 22 people and 8 people agree to vote for Mr. Tan. Does this suggest that Mr. Tan's case is justified at the 5% level of significance? Okay, what does it mean? So, he claims that he has 60%, right? And then our H1 is P less than 0.6, okay? 0.6. So level of significance is 5%. So less than, so meaning that we will look through one tail test on left hand side only. Okay? Let X be the number of people who vote for Mr. Tan. Therefore, this is binomial distribution. So 22. So P is the success, right? P is the success. If hash node is true, then X binomial 22 0.6. If hash node is true, but then given that 8 people agree to vote for Mr. Tan, so you have to find the probability, right? Probability, okay. 8 people agree to vote for Mr. Tan. So these are the probability 0.0215. Okay, 0.0215. All right. The test value X will lie in the critical region if P X less than X is less than 5%. Okay, and then we will reject P X less than X less than or equal to X less than 0.05. All right. What does it mean? Okay. Where is the graph here? They don't have the figure graph here. Okay. Right. Since this value is 0.05, less than 0.05, less than 0.05, so meaning that we will, where is it? Okay, the test value X will lie in the critical region P X less than or equals to X 5%. Reject hash node if probability of P X X is less than 0.05. Since this one is 0.025, where it is less than 0.05, then we will reject hash node. Okay. Alright, so meaning that Mr. Tan's claim is not justified. He is overstating his case. Yeah, he is overstating his case. Alright. We will reject hash node. Okay, how about for population proportion for large sample? When n is large, it is useful to use the normal approximation to the binomial distribution. Okay, this is when your binomial distribution, the size is too big, too large. So we approximate it to normal approximation, to normal distribution. Let X be the number of success. Okay, so this is your binomial distribution. If NP greater than 5, NQ greater than 5, then your binomial distribution can be approximated to normal distribution. I'm very sure that you have learned this before, right? In the binomial and normal distribution chapter. Then when testing population for large sample, hash naught P equal to P naught is assumed to be true, and the test statistic is given by X minus NP naught. NP naught is mu, NP, but then it depends on the P naught. And then standard deviation is a set of NP naught, Q naught. Okay, this is your test statistic. Right? Since the binomial distribution is discrete and the normal distribution is continuous, thus a continuity correction is needed. Okay, this means that if your x is 22, okay, because it's discrete, so 22, 23, 24. So when you approximate it to normal, and then you want to find the probability of px greater than 22, greater than. So meaning that you have to consider the continuity correction, plus minus 0.5. Okay, let's look at the example here. An investigation into the ownership of mobile phones among school children, 300 randomly chosen school children were interviewed and 224 own a mobile phone. 5% level of significance, null hypothesis given, and then alternative hypothesis also is given. So hash naught is equals to mu equals to 0.7, and then your hash 1 is mu greater than 0.7. Okay, that one is easy. It's already mentioned there. Alright, okay, greater than. So greater than meaning that when you draw your graph, you will just consider on the right side, and your level of significance is 5%. Alright, so now because this is a binomial, 300p, okay, so if hash naught is true, then p is 0.7. Okay, since x binomial 300 0.7, here should be np, right? Np for binomial. Since np greater than 5, nq greater than 5, so we can approximate this binomial distribution. So how we approximate? Okay, so this one is np 210, you can get by n times p. 63, how you get is n times p times q. 300 times 0.7 times 0.3, then you get that value. Alright, then after you normalize, then you find the test statistic. So x minus mu over standard deviation, 63, right? So you will get 1.701. Okay. Reject hash naught if z is greater than 1.645. Okay, where does this come? Because we know that our level of significance just now, what is the value? Is 5%. 5% is 0.05. 0.05, 0.05. Okay, since this is our z, okay, 1.701. Okay, 1.701. All right, so your z is 1.45. This is based on your right hand side. Okay, right hand side, because it's greater than, now p greater than, right hand side for level of significance 0.05. So it's 1.645. Since your z value 1.701 and it is falls inside, okay, inside your rejection region, because it is greater than 1.645. Okay, so if it falls in the critical region, then we will reject our hash naught. Okay, so we will reject our hash naught. And then one more thing here is, because this is binomial, all right, this is binomial, so the question just now is to find the probability 2 to 4. Okay, 2 to 4 on a mobile phone. Okay, 2 to 4 of them. 2 to 4 x greater than 2 to 4. This one, the A part. 2 to 4 equal. So using considering the continuity correction, so you have to consider 0.5 before 2 to 4, which means that your x must be greater than 2 to 3.5. Okay, all right, understand? So you have to consider this 2 to 3.5. So this is your x. 2 to 3.5 minus 210 divided by 63, then you get 1.70. So since z is greater than your level of significance, then the sample value of 225 at 5% level of significance is in the critical region. Okay, is fall in the critical region. So we can say that we reject our hash note, and it is conclude that more than 70% of the school children on mobile phone, because we accept our hash one. Right? Oh, that's all. That's the part 3 of the last part for the video. Okay, so I will give you more example, more question in the tutorial session. So make sure you have not so many. I think only 5 questions. Okay, good for your exercise. Okay, so you just look through the example again, and then if you have any problem, then you just discuss on the Padlet later. I will paste on our in our smart video. All right, thank you. See you. Bye bye.